So today's presentation, I've talked about it being a bridge to a cleaner energy future. So first I want to start and talk just a little bit about Enbridge as an organization. Our name actually spells out our mission, which is a bridge to a cleaner energy future. That bridge safely connects millions of people to the energy they rely on every day, and it fuels quality of life. Throughout our history, and especially today, we're looking beyond the horizon to invest in and build modern infrastructure, resilient communities, and reliable energy. We operate across North America and beyond, and we have 4 core businesses: our gas transmission business, our gas distribution business, our liquids business, and our power business. We move about 30% of the crude oil produced in North America on our system. We transport nearly 20% of the natural gas consumed in the United States. And we operate North America's 3rd largest natural gas utility by customer count. We're actually the largest in terms of throughput. We were an early investor in renewable energy, and we have a growing offshore wind portfolio. As a diversified company, we're uniquely positioned to help accelerate the global transition to a cleaner energy future, and we're doing it in ways that are ethical, sustainable, and socially responsible. We're advancing a number of low-carbon technologies, including renewable natural gas, carbon capture and storage, and hydrogen, which is what we're here to talk about today. We're committed to reducing the carbon footprint of the energy we deliver, and we're committed to achieving net zero emissions by 2050. That's our goal. We're headquartered in Calgary, Canada. We have a workforce of more than 12,000 people. So we're leveraging our assets for low carbon growth. This slide, I'm not going to rinse the whole slide, but I am going to talk just a little bit about some of the things that we're working on across the company in our, I'll call it our hydrocarbon businesses. So our gas transmission and gas distribution businesses, we're looking at multiple hydrogen studies. We've got renewable natural gas projects underway. We're doing carbon capture and underground storage, both down in the Gulf Coast and in southwestern Ontario. We have a number of solar self-power projects underway on our U.S. transmission system. In our liquids pipelines business, we've got carbon capture and storage again, a number of solar self-power projects, some of which are actually in operation now, powering some of our pump stations on our U.S. liquids pipelines business. One of our latest projects is at the Ingleside Energy Center near Corpus Christi, Texas. And this is going to be a low carbon, blue hydrogen and blue ammonia production facility with up to 95% of the CO2 produced sequestered in existing underground formations. So these assets are critical to enabling the energy transition, and we see it as a tremendous opportunity for us. As one of North America's premier energy infrastructure players, we have the capabilities and the expertise needed to advance low carbon investments. One of the things that we are doing is we're collaborating with partners to extend our capabilities, as well as our access to technology and complementary assets that further extend our opportunities. We're supporting this transition to low carbon economy through innovative energy solutions to keep energy affordable and reliable and reduce environmental impact. And we can't forget renewables. Renewables are a growing part of our overall corporate portfolio, and they have a number of advantages for us. They give us the flexibility to use our system in the future with electrolytic hydrogen. We have an opportunity in the future to use our ammonia export facilities to export hydrogen as markets form. We're looking at opportunities within some of our transmission system to blend hydrogen. And we're looking at opportunities to extract hydrogen at one of our processing plants to be able to pull it out of the stream and then create a marketable commodity separate from the natural gas stream. So there's a little bit up here. Our offshore wind strategy, we have a significant portion in Europe. And then we have a number of front of the meter and behind the meter strategies in North America. So behind the meter is self-power. Front of the meter strategies is things that are out and basically tied into the grid. So we have a significant number of opportunities in development. We have a number of facilities in operation, and we have significant future opportunities. We'll move a little bit towards my home, so to speak, at Enbridge Gas Inc. I started there 30 years ago in a legacy company called Union Gas. And Enbridge Gas, through amalgamation, has become North America's largest natural gas storage, transmission, and distribution company. We are the largest, as I mentioned earlier, in terms of volume send out. We do about 1,950 BCF per year of send out. We're the third largest in North America in terms of customers at 3.9 million. We meet 40% of Ontario's energy needs. Maintain almost 30 billion in assets, 154,000 kilometers of pipeline, everything from 1.25-inch plastic to 48-inch steel. We have 288 BCF of underground natural gas storage, primarily in the Sarnia area, and 800,000 horsepower compression. The Dawn Storage Hub, one of the top 5 natural gas trading hubs in North America, is an important link in the movement to natural gas from Western Canadian and US supply basins to markets in central Canada and the Northeast US. And certainly in the last 25 years, I've seen a significant change in the operation of that facility in terms of how it interacts with the producing basins within the Western Canadian basin and the eastern half of the United States. The company has facilities in 88 locations, 3,880 employees. We operate in over 670 communities within 313 municipalities and more than 20 Indigenous communities. What we're really engaged in now is innovating and adapting our business model to accelerate the transition to net zero. And we're focusing in 3 areas. We're looking at using less through conservation. So we have programs for residential, business, and industrial customers. Our customer base ranges from everybody from folks that have a condominium to large refineries, automotive plants, large power plants. We've got the whole gamut in Ontario. We're looking at the transition to renewable gases. So we have made significant investments and will continue to in renewable natural gas. And obviously we're expanding into the hydrogen space, which is what we're here to talk about today. And then we're advancing clean technologies for transportation, building heat, and industrial processes. So things like CNG and RNG for vehicle fuel, hybrid heating, geothermal, and carbon capture. So what we're here to talk about today, investment in hydrogen. What are we doing in the hydrogen space? So these are some of the more significant projects that we have underway at the utility for hydrogen. So we have, and it's been in operation since 2018, a power to gas pilot project in partnership with a company called Hydrogenics. This was the first North American utility scale power to gas facility. It's a 2 megawatt electrolyzer. It provides hydrogen energy storage, and it's produced about 300,000 kilograms of hydrogen since its inception. In 2021, we brought into service our Markham, Ontario blending pilot project. This was North America's first hydrogen natural gas blending facility in a distribution network. What we do there is we blend up to 2% hydrogen for 3,600 customers. And what we see is a 97 to 120 tons carbon emissions equivalent annual avoidance potential there. And I'll be talking a little bit more about those two projects in tandem in a couple of minutes. We also have a project in development in Gatineau, Quebec. It is a blending project similar to the Markham, Ontario project. We're looking there at blending up to 5% hydrogen. It has the potential for up to 43,000 customers. It's a much larger electrolyzer, 20 megawatts, and about a 15,000 ton annual emissions avoidance potential there. And the last project that I'll be talking about today is our Parkway turbine operation. So what we're looking at there is a project to reduce our own use fuel, reducing our scope 1 emissions. And it's a 5 megawatt waste heat recovery. And then the turbine there basically will end up operating on hydrogen blended fuel. So I'll be talking about the Markham power to gas and the Parkway turbine operation. Today, the Gatineau project is very similar to the Markham blending one. So let's talk about power to gas, because I think this was a really unique opportunity for us. We developed and built this in Markham, Ontario, and it's a project that's co-owned with a company called Hydrogenics. And what we do here is somewhat unique. We're tied into the grid and connected to the grid operator. And what we do is we balance the grid by responding almost instantaneously to variations in supply and demand to regulate the grid. So working with the electrical operator, if there's an upset, an industrial customer comes offline really quickly, or something happens with a generator, we can adapt the amount of energy that we're absorbing into this electrolyzer almost instantaneously, within 1 to 2 seconds, and help work to stabilize the electric grid. It's a very useful tool for the grid operator, and it essentially gives us the opportunity to create essentially what could be called green hydrogen. So what we do here in the power to gas facility, we enable the storage energy. We basically convert electrical power via electrolysis of water into hydrogen and oxygen. Right now at this facility, we're not utilizing the oxygen. The oxygen is actually just vented. It is very wet. It needs some additional processing before it would be considered industrial grade or medical grade oxygen. So at this point in time, we haven't installed facilities to do that for the oxygen, but we are capturing the hydrogen. And we're capturing that hydrogen in storage tanks. And then some of the uses that we've envisioned for that hydrogen that's stored in the tanks includes the blending, which we're going to talk about in a moment. There's potential for electricity generation from hydrogen via fuel cell. And we're also actually installing a natural gas converted ICE generator there to run on hydrogen fuel as well to power a local building. And then also as industrial process feedstock, although it does require a little bit of additional processing. We've looked at it using it as transportation fuel as well, but the purity requirements for transportation fuel will require some additional work before we can get to that point, because there's additional processing required. So what did we do with our blending project? We started with an engineering assessment. So we went through a 5-step process to review all of our equipment and the entire hydrogen blending scope. And I just want to walk through some of the steps that we took. So we really started with due diligence. We completed an engineering assessment to determine the maximum amount we could blend into our grid. And through these 5 work streams, we reviewed R&D, we did asset evaluations, we looked at end-use equipment, we looked at our pipelines and stations, and then we did a risk assessment too. So I'm going to walk through some highlights of each of those 5 work streams. First is R&D initiatives. And I'm not going to rinse the R&D initiatives either, but suffice it to say that's a very busy slide. And I think that's important to understand is there's a lot going on in the industry right now around hydrogen. There's a lot of research. There's a lot of new information coming to light. There's a lot of new opportunities, a lot of new equipment coming on the market. There's all kinds of things happening within the hydrogen environment. So just really quickly, we were involved in R&D. We were involved in a CGA, AGA task force. And that looked at the impacts of blending hydrogen into natural gas infrastructure. It identified some due diligence activities. And really what it looked at was a hydrogen blending percentage from 0 to 5. So that was really the focus of the R&D that we did, was up to 5% blending. There were some joint industry projects, HyReady, which was an joint industry and supplier joint effort, and that was really to try and bridge the gap between R&D, the theoretical, and operations, so the actual practical in the field. So by having distributor involvement or natural gas distributor industry involvement and supplier and other involvement, we were able to, bring that translation of the R&D into the practical world into effect. And we looked worldwide in projects that were under development. So we looked at, in Europe, there's a lot of work going on in the hydrogen field. And one of the things that I found really interesting was hydrogen blending is not actually all that new. In the middle of the 20th century, particularly in England and Germany, there was a lot of coal gas used, a lot of manufactured gas, and it was colloquially known as town gas. So there's some history with using blended gas streams in appliances and other pieces of equipment. In fact, the German gas composition into the 1960s was as high as 50% hydrogen, what they were burning. Low BTU content, had a bunch of other stuff in it too, carbon monoxide, carbon dioxide, and so on. But there certainly was some experience that we could draw on there in terms of the impact of gas blends and varying gas compositions on end-use equipment. And that's work that are things that were going on 60, 70 years ago. So one of the things we were after was an isolated area, a closed blending area that we could work on. And it's a little bit difficult to figure out what's going on this slide, but it's primarily a map of the North Toronto area. And what we were looking for was a loop or a section of our distribution system that we could isolate and inject hydrogen into, and that way we could, keep it contained, and we could also monitor it, easily monitor it, and make sure we knew what was going on. So we evaluated 8 loops within a reasonable proximity to our hydrogen production facility. And we were really looking for those closed, controlled loops that we could really keep a close eye on. So by doing that on an isolated basis, it gave us the opportunity to assess the network effects, right? So that whole monitor, learn, mitigate, adjust, or the plan, do, check, act. It would make it much easier to enact that cycle. So we did an evaluation matrix. We looked at the number and type of customers, consumption, vintage of the pipeline equipment, number of pressure cut stations, the distance from our facility, and we came up with 8 loops. And we recommended one large loop, which we then broke down into 3 sub-loops. I'm going to try this, the laser pointer from here. But our facility is right here. That is where the hydrogen blending facility is. And the 8 loops, you can see them marked on the screen here. But this was the loop that we ended up picking. And then we broke that loop into 3 subloops. So this loop here, and this loop here. But as of right now, we are only working on this loop right here, loop S1. That is our pilot project, and it contains about 3,600 customers. It had the built-in advantage of being essentially right next door to our hydrogen production facility, which made the pipeline really short. If you look at the picture here in the top right, this is our blending facility. So it is a relatively standard natural gas pressure reduction station with a hydrogen injection facility. And these 2 white tanks right here, those are the hydrogen storage tanks from the electrolyzer. So as I said, the pipeline was pretty short, about 40 feet, which made it an ideal candidate for doing hydrogen blending. So we selected this loop. One of the things that we wanted to look at, though, within this, not only the close proximity, but also some of the other material characteristics, which I'm going to talk about a little bit more here, just comparing those 3 subloops. So just some material breakdown. The loop S1, the one that we actually picked, is almost entirely plastic pipe. It's got a little bit of steel pipe in it. So it's very homogeneous, which is an advantage because it cuts down on the number of different materials you're looking at. The services within that, we basically have 3 types of services: plastic, steel, and copper. And almost entirely, that S1 is all plastic services. So that particular area was constructed and installed over a fairly short period of time. So it is very homogeneous. The pressure cut stations and customer stations, there's not a lot of variability there. It's mostly single manufacturer componentry, which also helps a little bit. We use service regulators from Brian Donkin, Itron, and Fisher primarily. And that particular loop had almost all one particular type. So it gave us an opportunity. Not only was it close to our facility, but it was also a very homogeneous area that we could work with. So obviously that cuts down on some of the risks. And as we were going through our research, we found out it's not just the hydrogen percent that's important. It's the effect on, it's a function of the partial pressure and the temperature. It's a function of operating conditions. So variable loads, localized stresses, and I'll talk a little bit about those when I get to the impacts on specific materials. There's microstructure susceptibility issues with steel or plastic. In steel, whether you're in the weld zone or the base metal because of the heat affected zone, and everybody's favorite, father time. How much are we affecting the total lifespan of some of this equipment? We looked at safety and risk, and as of the current research, stratification of mixtures of hydrogen and methane have not been observed in pipelines. They tend to operate as a homogeneous mixture, similar to the way that natural gas usually has trace amounts of propane and heavier hydrocarbons in it, and a little bit of CO2, and you don't see stratification within the blend. Same thing happens with hydrogen. So the assumption going in was that if a fitting is natural gas type, it's hydrogen type. So that blended gas stream is not going to preferentially bleed hydrogen through a fitting over natural gas. And then the third thing, and something that's always of concern in the natural gas industry is explosive limits. So lower explosive limit and upper explosive limit. And I apologize if the numbers are a little small there in the corner, but straight natural gas is an LEL of 4.87, just under 5, and a UEL of about 14.88. So that's 5 to 15% gas is the explosive range. For the 5% hydrogen blending that we were looking at, it really doesn't change a whole lot. the lower explosive limit drops down to about 4.82, and the upper explosive limit up to about 15.5. And even up to 10%, it really doesn't change a whole lot either, 4.77 to 16.1. Not really a huge change. Obviously, 100% hydrogen is a whole different story. Its explosive range is 4 to 75%. So that's one of the challenges with hydrogen, is the wide explosive range of hydrogen relative to what we're used to in the natural gas industry of that 5 to 15. So it's interesting to note that this slide has a number of assumptions based on current research. And I was talking to Peter Roth from Sundyne last night. All of this might be different by Friday, because there's so much going on in the industry in terms of research and development that this is what we know today. Actually, what I knew last Friday when I finalized this presentation, to be honest. So I'm going to move on to hydrogen's impact on steel. So ductility, fracture toughness, and fatigue are sort of the three things that we want to look at when we're talking about steel pipe. And it all boils down to hydrogen embrittlement. It's interesting because if I think back to the materials that we had in the 1940s and 1950s and all of the work that we've done over the last 70 years or so to improve the ductility and fracture toughness properties of steel pipe, hydrogen does a whole lot of things to sort of back off on all of that development. So that it acts exactly in reverse and actually causes potential hydrogen embrittlement. So it's something that we have to keep track of. The interesting thing that I found out working through hydrogen is that hydrogen embrittlement, stress is a big factor in hydrogen embrittlement, and it's changes in stress. And we always think in business about changing pressure. So the pressure changes, the stress changes. But even if the pressure is constant, if you've got external stresses, and it made my head hurt because I had to go back and think about more diagrams again, but if you have external stresses acting on that vessel, then that actually vessel or that piece of pipe, that actually creates changes in the stress environment and can lead to crack growth, even though you're keeping your operating pressure constant. And that's sort of the standard thing. Well, we'll keep the pressure the same, that'll keep the stress the same, but it really doesn't. Loading on pipelines, loading under roadways, loading from soil changes over seasonal fluctuations and so on can create changes in the pipe stress and create issues with hydrogen, even if you keep the pressure exactly constant. So what we're doing in terms of next steps, a lot of materials testing, a lot of sensitivity studies. And we're undertaking a number of those internally and with partners. Some of the things that we may need to do is look at some section replacement with the higher blend ratios. So as we move beyond 2%, we get to 5, and maybe move to 10, we may have to make some changes to the steel pipe that's in the ground. The other materials that we're involved in, so polymers. There's two industry standard tests on polyethylene: slow crack growth and oxidation induction time. Those are sort of two standard polyethylene test results or test regimens. And that really looks at fracture crack propagation in plastics and the depletion of the antioxidants. So anybody who's got some of that white plastic lawn furniture at home knows what happens when it sits out in the sun too long. It starts to get chalky. Well, same thing happens to natural gas piping, polyethylene piping underground. The same kind of activity occurs. And then the slow crack growth, we think about cracks in steel pipe, but actually plastic pipe can do the same thing. It can elongate and get stress cracks in it. So hydrogen does have an impact on both of those. And again, it's down to more evaluations, more study, and more trying to understand the impacts of hydrogen interaction with those materials. And then the last thing is our soft goods, our elastometric materials. You know, in a natural gas distribution network, you've got lots of that. Every service regulator's got a diaphragm in it. There's lots of O-rings in some of the connection equipment and so on, especially on the low pressure side. So we're looking at those in terms of crack growth, plasticization, and leakage rate. So is there any membrane leakage rate through those elastomeric materials? You know, what's the impact? Does it cause swelling or bulging in the material because of changes to the plasticization? Does it cause cracks? You know, the last thing you want in a rubber boot regulator is to find out that things swelled up and cracked. So it's certainly something that's of concern and something that we're tracking. Which leads me to the last part of this, which is our risk assessment. And we did risk assessment activities both internally and externally using consultants. And we looked at all of our piping and equipment. So right from our network through to the customer's internal piping in houses and down to their appliances. We looked at a whole pile of different things. We looked at any general hydrogen effects or hazards. We looked at, within the customer premise, any impacts around releases, interior releases in buildings. We looked at our hydrogen blending station, were we introducing incremental risk into it? The district stations, so the stations downstream where pressure cut stations within the network, impacts to those. The mains and the services, so the plastic main, the steel main, the steel and plastic services. And any worker safety and human factors too. Whenever you're involved in a network like this, there's human factors too. So we did indoor release modeling with our end-use customers because that is probably the area we have the least amount of control. And we really found that it had minimal effect on the duration required to meet lower explosive limits. There wasn't really any significant changes, to toxicity or anything like that. So that was good news, but we're still monitoring. And then we did a full quantitative risk assessment. So really what we were trying to do with an external consultant was understand, by doing this blending project, are we increasing the level of risk to our system? Because if some of my colleagues here in the room know, one of the things that Enbridge is really averse to is increased risk. So we really take that seriously because we don't want to do something to increase the risk either to our operations or to the public. So we did a quantitative risk assessment. We looked at the system as is, and we looked at the system post-blending to see where we were going to potentially increase our risk. And then, out of that risk assessment, we looked at risk mitigation actions. So some of the things that we decided we were going to do within this network, specifically over and above, were different than what we do in the rest of the network. We had a specific operational and risk integrity management program for this particular area. And that's really to quantify the safety and reliability. So really watch this particularly closely. So we're monitoring leak frequency of the blended network and comparing that to what we would expect to see if we're seeing more leaks. So we made assumptions. Gas type's gas type, whether it's gas or blended hydrogen. Is that going to play out? So we're monitoring actively for leaks that are detected to make sure that we're not seeing a significant uptick. We're accelerating the replacement of some of our fittings that we think may be susceptible. They're susceptible to potential leaks in the natural gas environment, so they're going to be at least as susceptible to leaks in a blended environment. We looked at a number of new procedures and amendments and processes. We amended our leak detection procedures. We looked at our emergency response and our related operational procedures, our gas control procedures. We did a number of things. Basically, we put processes in place so that any new commercial or industrial customers are aware of the fact that they're receiving blended hydrogen and it's not just a regular natural gas service. we looked to make sure that the system really was isolated. So we made sure that we didn't have any bypasses or emergency backfeeds and so on. We took all of those out of the system so that nobody can inadvertently change the system back to natural gas through operational activities. We put a moratorium on the addition of new CNG stations or NGV refueling stations within that network, simply from the perspective that their sensitivity to hydrogen is not really understood without some further study. So again, as more studies go on and more information comes to light and the industry gets more comfortable with blended hydrogen in CNG, then maybe we'll relax that. But for now, we've put a moratorium on new CNG refueling within that loop. And then when we get material faults, we're assessing those in the context of hydrogen blending. So we're doing a little bit different material assessments on things that come out of that are reported out of that area to see if there is hydrogen impacts on whatever happened to be failure. And then lastly, we've got a process in place to monitor the increased volumetric demand. So we have expectations for what a blended network will use for consumption, and we're comparing that to very similar areas nearby and making sure that the assumptions that we've made around increased consumption are actually bearing out. And we do actually adjust all those customers' bills too. All those customers get a bill adjustment to account for the fact that on a volumetric basis, the gas they're receiving has got slightly lower BTU content. So that's our blending project. We're looking at opportunities to expand that as time goes by, but for now we're starting small and as I mentioned, we're looking by 2025 to have a project in service in Gatineau, Quebec. And it will be a larger project and it will be a little bit larger in scale and scope. The idea is we're taking all the lessons we learned from this pilot project and applying them and scaling the thing up. So the next project I want to talk about, it's got a little more of a compressor flavor to it, since this is the compressor tech forum. We're looking at a scope 1 emissions reduction at our Parkway C facility. So our Parkway facility is on our transmission system, and it's an interconnect facility in Enbridge Gas's transmission network with TransCanada Energy and with our own Greater Toronto distribution network. And part of this facility includes a large pressure reduction station, which was key to this whole project. So if you look here, let's go back. There we go. Sorry, push wrong button. This is a pressure reduction station here. It feeds our Toronto network. We have 2 compressors here and here in this facility. There are 2 more on the east side of this highway. The highway actually splits the facility, and there's 2 more on the east side of the facility. This picture here is a close-up of Parkway C. That particular facility is a Rolls-Royce or RB211, or now known as a Siemens AGT35 aeroderivative gas turbine. It's one of 4 units at that facility. There are 3 of those and 1 Rolls-Royce Siemens Avon engine. The 3 RB211s or AGT35s are all DLE technology. The Avon is conventional combustion. Parkway C facility was selected for this particular project because of its operating hours profile. So it's one of our most used engines, and its proximity to the pressure reducing station. So this is generally what we're doing. We're adding a turbo expander at that facility. If you look at the gray lines, that's all the existing piping network at the facility. So the incoming stream, part of it goes through a distribution regulating station and out to the low pressure distribution. When I say low pressure, I mean 275 PSI or 19 bar. And some of the stream goes through compression and goes out to our high pressure transmission customers. So what we're adding here is the red line. So we're adding a waste heat recovery unit off of the turbine. and then a turbo expander to operate in parallel with the distribution regulating station, and then feeding that gas back into the low pressure distribution station. The turbo expander is sized for our summer load at the facility, which is about 40% of the peak winter load. So we've got some potential options for expansion over time if we feel like it. But we're sizing it to manage the entire summer load, which is about 40% of the total. The turbo expander will drive a generator, which will power an electrolysis facility. There's a small H2 storage facility on site, and then that electrolysis, the hydrogen produced by the electrolysis facility through the storage facility will end up being injected into the fuel gas stream for the SGT-35. Jack's giving me the look here, so I'll try and finish up here in a couple of slides. A few engineering considerations that I wanted to make sure that we talk about. So some of the things that we came up with, and I'll run through this fairly quickly, and I'll get to some performance here in a minute. Electrical component certification is a big deal. So depending on concentration, your Class 1 Group D devices for natural gas, hydrogen's a Class 1 Group B. So there's some changes required there, or some mitigation efforts to get you away from being in Class 1 Group B. The fuel gas. So hydrogen has a lower heating content volumetrically than natural gas, so your fuel gas skid needs to be adequately sized to handle the additional volumes. There's material compatibility issues. We've talked about some of those on the distribution network. Some of the same stuff applies here. And then purge requirements to remove H2. If we have an ESD scenario, we don't want H2 sitting in the fuel gas system on the skid. So there's a requirement there to purge that. Fire gas detection changes. Fire suppression system needs to be a little bit different. The detection equipment needs to be able to understand, or to be able to detect the modified flame that you'll get out of the hydrogen blended combustion if you happen to have an incident within the skid. There's additional requirements for ventilation. And your control system needs a lot of changes as well. The control system needs to understand the percent of hydrogen that's being injected into the fuel gas stream, and it needs to understand how it needs to feed fuel to the engine to be able to continue to operate. So from an expected performance perspective, the changes that we're making are expected to not negatively impact turbine performance. So we're looking at a hydrogen production rate of up to 100 kilograms per hour, or potential for about 20% blend at full power. And it does increase the fuel flow rate, like I said, so that has an impact on the fuel gas skid. It decreases CO2 as the H2 is increased. So a 20% blend, which is our target, is roughly a 16% increase in fuel flow, volumetrically, and a reduction of about 7% of CO2. I don't have NOx on here. There's a little bit more uncertainty around NOx, but the NOx is not expected to increase and potentially decrease slightly as well. So that's what I had to present to you today. In summary, I think these are really exciting times for the industry. There's a lot going on. There's a lot of really good work underway, and I know there's a number of folks going to present later today on a whole bunch of the things that they're up to, which I think is really going to be interesting and is going to create a lot of opportunity in the industry. It's an emerging area, so something that has a long runway in terms of where it's going to go. There's lots of research. I mentioned it earlier in the speech. There's a lot of research. There's a constant change, and all of us as participants need to stay on top of what those changes are. So forums like this are an excellent opportunity. And I'm not sure anybody knows exactly where it's going. I think I got a better chance of, I mentioned it last night, I got a better chance of figuring out my bracket for next year's March Madness than I have for exactly what this is going to look like in 5 years. But it's exciting. And I thank you for giving me the chance to talk this morning, and I look forward to the rest of the day. Thank you very much. Yeah, so Jack, I did mention too, Q&A wise, I'm around for the rest of the day. I'm more than happy if you want to catch up with me, stop with me during a break or lunch or whatever, I'll be happy to chat. Thanks, Jack.